Welcome to the first video in my course on data structures. The big idea I will be exploring in this series is how to design custom data structures. Take a look at video 0, the intro to the course, for a full explanation of the prerequisite knowledge and the main topics that will be covered throughout the course. To get started, I'm going to introduce a thing called an arity object. At one level, arity objects form a class of abstract mathematical objects, but we're going to make them more concrete by designing a few data structures to encode them. There are a few reasons to study arity objects at the outset of this course. For one thing, we're going to see that they have features of both binary trees and multisets. But to encode arity objects, we're going to have to fuse a tree and a multiset into a single structure in an appropriate way. This makes arity objects a nice, clean first example for how to design more complex data structures. Secondly, beyond just working as an example for practice, arity objects are worth knowing in their own right. Practically, arity objects resemble a type system, making them a nice starting point from which we can easily see how to build something like the C-type system. And more abstractly, when it comes time to learn about designing data structures with algebraic type notation and arrow diagram notation, arity objects are going to give us a map from concrete techniques to the abstract planning tools. In the second half of this lesson, I'm going to introduce the first data structure design technique of the course. In particular, I'm going to design a node structure for encoding arity objects. I'm going to show the data layout and then the core operations on that structure, and then finally I'll reflect on the pros and cons of the node structure for encoding the arity objects. Now let's get started with arity objects. I first learned about arity from a book called Programming in Martin Loft's Type Theory by Nordstrom, Peterson, and Smith. Arity was used by Per Martin Loft to describe the way that a piece of syntax could be classified. The core idea being some pieces of syntax stand for constant values, but other pieces of syntax stand for operators that have to first be supplied with yet more pieces of syntax, and then they can stand for a value. And arity classifies all of these pieces of syntax. The arity objects I'm going to introduce today are modified from that source, because mine are in a sense unordered arity objects. But for the rest of this video, I'm just going to simply call them arity objects. It might be helpful to think of arity objects as a property of operators. A unary operator and a binary operator have different arities. Now, arity also classifies values, but in this view we can think of a value as an operator with 0 inputs. I'm going to depict arity objects with pictograms like this one here. The first arity object I'm introducing to you is a single point, and this is the arity for a constant value. 2 points together is the arity for a pair, 3 points is the arity for a triple, and in general, for any positive integer, the arity of a k-tuple is just k of these points. If we think of operators as transformations mapping inputs to outputs, then a reasonable pictogram for the arity of an operator would be an arrow. A unary operator takes in one value and outputs one value, so the arity pictogram for a unary operator would be an arrow with a single point on the input side and a single point on the output side. Similarly, an arity pictogram for a binary operator is going to be an arrow with 2 points on the input side and 1 point on the output side. We can also write down arity objects for operators with multiple outputs by simply putting more than 1 point on the output side. To make arrows fully generalized, we can say that any two arity objects can be joined together with an arrow to make a new arity object. That gives us a way to create arity objects for higher order operations. But when we're writing arity objects for higher order operations, we're going to have to be clear about which arrows are inputs or outputs to other arrows. For instance, there are two different arities that can be formed from the singleton arity and the one in, one out arity via the arrow. The first is the arity for an operator that takes in a value and outputs a unary operator. A significant example of this kind of arity comes from function currying or partial function application. For instance, we could imagine an operator which takes in a number and outputs the operation that multiplies by that number. Normally multiplication is a binary operator, but after partially applying it, what's left over is a unary operator. The second is the arity for an operator that takes in a unary operator and outputs a value. You can find operations like this in lots of interesting places, but two examples are audio processing and animation systems. In audio processing, a signal, or you might think of it as a mono audio track, can correspond to the singleton arity. And a filter, which takes in a signal and outputs a different signal, can correspond to the unary operator arity. Then there's an operation that measures a filter by sending the so-called impulse signal through the filter. This measurement operation takes in a filter and produces a signal. Or, in animation systems, interpolation functions, which take in values on the range from 0 to 1, are very commonly used modeling tools. With such functions, you might like to ask questions like, what are the minimum or maximum value that this interpolation function can achieve on the unit interval, or what is the average value on the unit interval, and so on and so on. The operators that answer questions like those are again taking in a unary operator and outputting a single value. So now, with the arrow, we can generate endless new arities, but we only have tuples for values still. What if we wanted a tuple of two unary operators, or a tuple with a value and an operator? To get arity objects for generalized tuples, we're going to say that anytime we have two arity objects, we can paste them together to make a new tuple-like arity object. The points and arrows in a tuple-like arity object can be drawn together in any order. We can think of these tuples as just bags of jumbled up pieces. So when we're pasting arity objects together, the order and nesting won't matter. Now we can make all sorts of compound arity objects with these construction steps. For instance, a test program that compares two implementations of the same thing may be thought of as having an arity like this, with two unary operators as input and a single value as output. Why is that? Well, if it's a test program that compares two other programs, those other programs have some input and some output, so each of them is an input to the test, and then the test either says one value, yes, this worked, or some other value, no, it didn't work, and here's where it failed. So in a way, we can think of this arity as representing the arity for a comparison test program. I'm also going to add an empty arity object to the definition. You can think of it like the zero of the arity objects. And to make it behave more like zero, I'll define some rules for how the nothing arity collapses when combined with an arrow or with pasting. First, an arrow from nothing to something is the same as having that something and no arrow at all. This makes sense from the perspective we talked about earlier, that values are like operators with no inputs. In a programming language with side effects, functions with no inputs are quite different from constant values because they can still depend on implicit context in the program. So if I wanted to capture that sort of distinction in my model, I would throw this rule out. Second, an arrow from something to nothing is the same thing as nothing. This makes sense from the perspective that operators map inputs to outputs, and so if they don't produce anything, they don't do anything. Again, there are absolutely contexts where an operator system might want to classify operators that consume inputs and do something to the implicit context or just destroy the inputs or something like that. And if I wanted to capture that possibility in my model, I would throw this rule out. Third, pasting nothing onto something leaves that something as it was. This makes sense from the perspective that adding nothing to a tuple shouldn't change the structure of the tuple. With these rules, the empty arity is prevented from introducing any new unique arity objects beyond itself. So with the exception of the empty arity, all other arities can be written without reference to the empty arity. Okay, so far what I've given you is an intuitive pictographic description of what arity objects are. Now I'm going to lay out a simplified, formal definition with a few key points. 1. There is a singleton arity object. 2. Given two arity objects, we may generate a new arity object by putting an arrow from the first arity object to the second. This operator is neither commutative nor associative. Since it's not commutative, that means the input side of the arrow is distinct from the output side of the arrow. And since it's not associative, that means that the binding of arrows within arrows is significant, and we can't exchange one binding order with another binding order. 3. Given two arity objects, we may generate a new arity object by pasting them together. The pasting operator is commutative and associative. Because it's commutative, that means we don't care if one arity or the other comes first in the operator. The order of inputs is irrelevant. And because it's associative, we also don't care about the grouping or layering order. As long as you put the same pieces together, you get the same arity object no matter how many pieces you put together. 4. There is an empty arity object which is not equal to any of the arity objects we can generate from the first three rules, and which follows these simplification equations. For the next few videos, we're going to study a handful of ways to encode arity objects. But why should we bother? For one reason, arity objects are going to make good practice. Arity objects sort of resemble binary trees and they sort of resemble multisets, but arity objects fuse both together. It's an idealized version of a more complex data structure compounding problem. Once we have techniques for encoding arity objects firmly in hand, we'll be able to use very similar techniques to encode type systems like the C-type system, and later the patterns we observe in the properties of arity objects will extend to data structuring techniques in all sorts of patterns. But arity objects themselves could be useful without modification in some cases too. For example, earlier I alluded to how arity objects could classify entities in an audio processing system or an animation system. With some simple tweaks, arity objects could classify commands in all sorts of user applications, allowing some commands to demand extra user input or restricting their applicability to only be bound to certain kinds of events. And even later in this series, a slight modification to arity objects is going to appear in a geometric construction application. So hopefully I've given you at least one reason that has caught your interest for learning arity objects and how to encode them. Now, take a minute and think. How would you create a data structure that encodes an arity object? If you want, now might be a good time to pause the video and make a list of the ideas that come to you. For this video and the next two that come after it, I'm going to be covering 3 ideas for encoding arity objects. First, I have a node structure, which is a structure made up of a single node type that can contain pointers to additional nodes to fill out complicated structures. Second, I have an expression encoding, which is a string expression syntax for encoding any arity object. And third, I have an index structure, which builds up arity objects inside of a context and allocates out small consecutive IDs and deduplicates arity objects on construction. For the rest of this video, I'll be covering the node structure. I want to start off with looking at the node structure because node structures are very flexible and often the easiest way to build a first iteration. Before I show how I designed my node structure, let's imagine for a minute what might happen if I approach this by trying to encode arity objects with some plain value representation. For instance, with just an unsigned integer, I could encode the values for tuples. 0 would stand for the empty arity, 1 would stand for the singleton value, and an integer k would stand for the k-value tuple. If I also wanted to represent the first order operators, I could extend this a little further. I could have a type with 2 unsigned integers, an input count and an output count. And since the input of 0 is the same thing as a constant, this single type would represent all of the value tuples and all of the first order operators. But either the move to encode higher order operators or the move to encode tuples that mix values and operators would push me beyond any plain value representation. To stick arrows inside of arrows arbitrarily, I need to replace the input count and output count with a full-on input arity and output arity. And to mix arbitrary combinations of arities into tuples, I need to be able to keep some kind of mapping from a collection of arities to these integer counters for each arity in the tuple. Neither of these can be represented with a plain value type because they both have some kind of self-compounding pattern. The arrows are putting arrows inside of arrows, and the tuples are using smaller pieces of arity in collections. So either way, we need something that can't just be a fixed size value. The whole point of a node structure is to embrace the self-compounding nature of the information in the most convenient way possible. A node structure in C uses pointers between nodes to link up compound structures. These pointers aren't just layout information like they might be in a basic array type. In node structures, the links form a part of the primary information of the structure. We can't just relocate nodes because we would have to update the link pointers throughout the whole network of nodes to maintain the meaning of the structure. To keep things simple, I'm going to use a style where nodes are allocated once on an arena, then left in place from then on until the arena memory itself is popped. Later, we'll look at more memory management techniques to use with node structures, but for sketching out Arity nodes today, I'm not going to worry about that. Now let's look at my Arity nodes. I've provided a repository with the full buildable example code in the description. The data structure I'm looking at today is found in aritynode.h and aritynode.c. I'm going to start off with a blank Arity node and then give it a kind. Each rule in the formal definition is going to give me one of the kinds of Arity node. I put the empty kind first, since the empty Arity is like 0, and nodes with this kind simply encode the empty Arity. Next, I add the singleton kind, and nodes with this kind encode the single value Arity. Next, I add the arrow kind. Nodes with the arrow kind are also going to need 2 pointers, one for the input arity of the arrow and one for the output arity of the arrow. So here I put the extra data for the arrow under an anonymous union, and these fields will only be valid in arrow-kinded nodes. Finally, I add the tuple kind. Nodes with this kind will need a collection of Arity nodes, which I could represent as an array of Arity node pointers. These collections could contain any number of duplicates, though, so for instance, the k-value tuple would have k copies of the singleton Arity node. This is a pretty space-inefficient way to encode the k-tuple, which might be something I want to encode fairly frequently, so I want to represent duplicates with a coefficient instead of with literal duplicate pointers. I could replace the array of Arity node pointers with an array of so-called parts and give each part one Arity node and a coefficient. And while that would have some advantages in its simplicity, it would mean dedicating 16 bytes to each part in a node. In fact, both the node struct and the part struct would have 4 wasted bytes each because of memory alignment. So instead of putting the coefficient into the array of parts, I decided to place the coefficients inside the nodes themselves in the unused 4 bytes that they already had after their kind field. This type definition code gives me an initial sketch of my data structure, but before we move on to look at the operations, let's look at a couple of examples of how these nodes will encode Arity objects. First, the singleton is quite simple. The kind is singleton, the coefficient is 1, and the other fields can all be left 0. Next, let's look at a 2-value tuple Arity. The 2-value tuple is encoded with a node of the tuple kind and a single part node. The part node has a singleton kind and a coefficient of 2. We can make the 1 in, 1 out Arity, or the Arity of the unary operator, with 2 nodes. The arrow itself is encoded with a node of the arrow kind, and then it has a domain and a codomain pointer which each point to a node for the singleton Arity. Next, let's look at this mixed tuple. To encode mixed tuples, we use multiple parts. Here the root node has the tuple kind, and the parts array has 2 nodes in it. One of the parts is a pointer to a node encoding a singleton with a coefficient of 2, and the other part is a pointer to a node encoding the 1 in, 1 out Arity, or the unary operator Arity, as we've already seen, and that has a coefficient of 1. As a final example, let's look at this Arity we saw earlier for the function comparison test, which takes in 2 unary operators and outputs a value. Its root node has an arrow kind. Its domain points to a node with a tuple kind, which then contains 1 part node for the 1-to-1 Arity and a coefficient of 2 on the 1-to-1 Arity. Then finally, the codomain of the root points to a node for the singleton. Okay, so I've covered how the Arity node is laid out in memory. Next, I need to design and implement an API for constructing instances of my data structure and running operations on it. I have my API organized into 3 sections: construction, operations, and helpers. The construction section is for building up Arity node instances. The operations section is for anything that computes with Arity nodes as inputs or outputs. And the helpers section contains supports for implementing the functions in the other sections. In the construction section, we have ds Arity node empty, which always returns an empty node. ds Arity node singleton, which always returns a singleton node. ds Arity node arrow, which returns a node that stands for the arrow Arity with the supplied domain and codomain. ds Arity node paste, which returns a node that stands for the paste Arity of the inputs A and B. ds arity node sum, which takes in a variadic list of coefficient values and arity nodes in pairs, and creates a tuple made up by pasting all of the input nodes together with their counts multiplied by their coefficient pairs. The list is terminated with a 0 argument so that we can tell when we've read all of the variadic arguments off of the VA list. And finally, there's the ds arity node k tuple, which returns a tuple containing a singleton with the supplied coefficient. In the operations section, we have ds arity node copy, which returns a copy of the input arity node, fully transporting all of it onto the new arena. And ds arity node equal, which determines whether the two arity nodes that are input to it stand for the same arity. Before I dive into the implementation of my data structures API, this is another good opportunity to pause and get some practice. If you want, you can try implementing some or all of the main API functions that I just listed. If you do implement them all, then you can run your implementation against the test code that I published with the repository. If you're interested in trying to run the test code and pass it, then I have a supplemental video for you with instructions on how to run test code for any of the lessons in this series. Now we're going to look at my implementation. The first 4 functions correspond directly to the rules defining arity objects, and therefore, as we saw, also to the 4 different kinds of node in the arity node structure. You can construct any arity with just these 4 functions, and so these are the 4 functions I'm going to review here. The other 2 constructors improve upon the convenience and efficiency of the basic constructors in some common cases. Since I'm building my data structures on an arena base layer, each of the construction operations takes in an arena. I have an implicit assumption about how arenas are used in this construction API, and that's this. Whenever a new node is being constructed that's based on some existing node, I'm assuming that the same arena was used for both the original node and the new node that's being constructed. And this is a rule that I commonly have to use in node structures. The implementations for the first 3 constructors are quite simple. In the first 2, I simply allocate a node and fill its fields appropriately. With the arrow constructor, I have to do a little bit of work to apply the simplification rules regarding empty arity first, but otherwise I again just allocate a node and fill its fields. The implementation for paste is a bit more involved, so let's first look at what it needs to do before looking at the final code. Empty arities are simply going to collapse away, so we can handle them easily. With 2 singleton inputs, the output is going to be a tuple with a singleton part and a coefficient of 2. If instead we have 1 singleton and 1 arrow for the inputs, the output is still a tuple, but now with 2 parts, 1 for each of the inputs and each having a coefficient of 1. If we have a tuple in the input, we want to decompose the parts from that input tuple and put them back together into the output tuple. In this system, we don't ever have tuples that act as parts to other tuples. Instead, each tuple stands as a multiset, and pasting things together is about combining the multisets. Whatever happens, we're making sure we never put 2 parts in the tuple structure that are duplicates. For example, if we have a 2 tuple and a 3 tuple as inputs, then the output should be a tuple node with a single part and a coefficient of 5. So we're being careful to deduplicate parts as we add them to the output tuple node. With the exception of the empty arity cases, this always returns a tuple kind node. So we can skip straight to asking how many parts we need to allocate for the node. We won't know this number until we've deduplicated all of the incoming arity objects, so we're just going to compute an upper bound and allocate that much on scratch. Then we'll fill the parts array up piece by piece, deduplicating the parts as we go, and incrementing the coefficients on accumulated parts. And then finally, once the final node part count is actually known, all the parts will be copied into a final destination array and placed inside a new tuple node. That's the idea. Now let's look at my code. First, I have a special case check for the empty arities. Next, I count the maximum number of parts that may be needed in the output tuple. Empty arities never get this far. Singleton and arrow arities can contribute at most 1 part each, and a tuple arity can contribute at most a number of parts equal to the number of parts in the input tuple. Next, I fill the output parts up with parts from the A arity. I don't need to start deduplicating yet because a single valid arity node can't contribute any duplicate parts. I use a helper here called part copy to shadow copy each node as I add it to the parts array. I do this because I'm building up this tuple and I could modify any of the coefficients in this parts array, but I don't actually want to modify the coefficients on the original nodes that I'm reading them from. The logic for adding in the B arity is similar to adding in the A arity, except at each step where I would add a new part, I first check if it's a duplicate to a node that's already in the parts array. The helper part find match does this task for me, actually. If I find a duplicate, I just increment the coefficient of the part that's already there in the output parts array. Finally, I determine the actual count of parts and prepare an appropriate output node. Okay, that's everything I'm going to review in the construction section, so next let's look at the operations section. The first function here is copy. Luckily, the arity node structure forms trees, so a simple recursive implementation gets the job done. For each node, all I have to do is copy over the simple values and then recursively copy the child nodes. If this node structure formed a graph, deep copying this way wouldn't work, but we'll visit the case of graph-like data structures later on. The second function here is equal, the equality tester. It's a little bigger, but ultimately not much more complicated. Since I've been careful to eliminate any possibility that a single arity could be encoded with two different kinds, I can start off by just checking that the nodes have the same kind. For empty and singleton arity nodes, that determines equality completely. For the arrow arity, I next have to recursively determine that the domains and codomains are equal. And for the tuple arity, I check that the A and B inputs have the same number of parts, and then I ensure that each part in A has a matching part in B with the same coefficient. And this part again uses the helper part find match. With that, we've seen the full arity node data structure. Now I'm going to talk about some of the pros and cons of this data structure, and I'm going to point out how many of the specific things I observe along the way about the arity nodes are also true of node style structures in general. In my opinion, a node structure is an ideal way to sketch out a new data structure. In this example, for instance, the code for the type definitions and the constructor APIs were written almost directly following my definition for the arity object. And in general, I find that node structures tend to make it easy to make the code reflect the notion of information that I'm trying to encode without having to deal with all the extra details that come with tighter data structures. And perhaps more importantly, node structures are flexible. And by flexible, I mean that if the notion of information that I want to encode is likely to drift over time, the node structure is usually the easiest way to update to the new definition. Smaller, faster data structures usually require the code to rely on using as much context as possible, which also means overfitting to the definition a little bit. And that means more work changing the code as the definition is changing. The example today didn't actually demonstrate this flexibility, but if you want to see it for yourself, try out this next exercise. Change something about the definition of the arity object and see if you can update the code to match the new definition. Or at least write a little bit about how you would update the code to engage with the idea of modifying the code to match a new definition. Here are a few suggestions of ways you could tweak the definition to generate this exercise. One idea is you could replace the single point-like arity called the singleton with a fixed finite set of distinct point-like arities. A second idea is you could redefine tuple-like arities so that order matters within the tuples. This would correspond to making the paste operator non-commutative but still associative. Or third, you could redefine the arrow-like arities so that arrows are bidirectional. In other words, you'd make the arrow operator commutative but still non-associative. Take any of those that you like and see what you come up with. Let me know how this exercise goes if you try it out. And in general, what I hope you'll find is that node structures like these are flexible. But inevitably, with that flexibility, there come some downsides. So let's have a look at those. First, it's a memory hog. Each node uses 24 bytes, and any interesting arities are going to use at least a handful of nodes. On top of that, each call to a constructor function allocates some new nodes, even if identical arity nodes already exist on the arena. And because of my factorization of coefficients, the parts in a tuple can't be reused from the inputs without first being shallow copied. While some of these issues could be addressed with deduplication structures and a change to the factorization within the structure, it's true in general that node structures that use full-width pointers to reference each other tend to be a bit fattier than other structuring techniques on the same information. Second, some of these operations have to work pretty hard, in particular the constructors for tuples and the equality operator. In their worst cases, both of these have to do n by m scans across a pair of part arrays. This could be improved by keeping those parts in some kind of sorted order. Then, instead of an O of n times m merging, the constructor could be using some kind of O of n plus m merging. In order to sort parts, we would need a computable total order on the arity objects. Or to put that another way, we would need to define a comparison operator on our arity nodes. There are multiple ways we could define a total order on the arity objects that would be computable, but I'm not going to cover the topic here because later I'm going to show you a different data structure design for arity objects that solves this problem without needing the total order on arity objects at all. And that method is just going to beat this method across the board. So if you want to explore it, this is another good opportunity to stop and try this out as an exercise. How would you define a comparison operation on arity nodes so that they could be sorted? A third point we can talk about regarding the node data structure is that it's an in-memory data structure. I often like to just call these hot data structures. A data structure is hot if it's wired up and ready to be used immediately in a program. Hot data structures exist at a specific place in time. You can tell that my nodes are hot data structures because of the fact that they use so many pointers, which are the main way to create hot structures in C. But hot structures exist in every language. They don't have to be based on pointers. They simply have to rely on whatever language feature it takes to make data ready to access. We can also talk about cold data structures in contrast to hot data structures. A cold data structure determines information in a way that is independent of position and time, and therefore ready to be transported. Since my arity nodes are a hot data structure, if I were going to transfer an arity object into a file, or over a pipe or socket, I would first have to put the arity object through a process of serialization. Serialization converts a hot data structure to a cold data structure while preserving the intended information, and serialization is typically defined with an inverse called deserialization that takes the cold data structure back to a hot data structure. The last con of this structure that I want to look at is that the complexity of the user construction code is pretty high. If I were going to specify arity objects as part of some larger system, having to construct those arity objects with this API would weigh it all down. It takes multiple lines of putting pieces together to build any interesting arity objects, and the final construction code obscures the nature of the object being constructed, making it hard to read and visually verify any of it. Furthermore, the code that constructs one of these has to be a procedural block, so that prevents placing any arity object as a data literal. While this issue doesn't impact performance or the ability to transport arity objects, it does impact the iteration speed of working with any system that makes heavy use of arity objects, and so on those grounds alone, I think that construction complexity is also worth considering. Alright, that's it for today. I've covered the idea of the arity object and its definition, and then the details of a node data structure that encodes the arity object. Next time, I'm going to cover a second data structure, an expression encoding for the arity object, and we'll look at how the expression encoding shifts the trade-offs of these various points that we looked at by comparison to the first data structure. So, see you then.